and welcome to the next in the series of weekly webinars that are offered by Exeter. The topic of this webinar is performing a cybersecurity risk assessment as a part of the component process hazard analysis. A couple of ground rules as we get started up here. Please mute your microphone and make sure that all of your speakers are enabled in your system. Hopefully you can hear me now, so that should be all taken care of. There's a question, a Q&A box at the top of your screen. Please don't hesitate to type in questions. I'll try to keep my eye on the question box as we go through and address the questions as they come up. The session will be recorded. Actually, it is being recorded, and it will be available on our website at the completion of the webinar. And all the slides will be available to everyone who has attended. So again, don't hesitate to ask any questions. I would be glad to entertain them. So as I said, the title of the webinar is Performing a Cybersecurity Risk Assessment as part of a component of the process hazard analysis. The original slides were put together by Hal Thomas. My name is Dave Johnson. I'll be giving this presentation today. A little bit about Exeter before we get started here. We are a worldwide company. We have international headquarters located in northern United States, in Pennsylvania, and also in Germany, just south of Munich. So Exeter is involved with the complete supply chain of functional, safety, and security-related applications across multiple industry sectors. From original equipment manufacturers, you can see in the upper left, to end users, which are in the lower right. Original equipment manufacturers are interested in certifications and various tools to support the products that they make. We also, like I say, we have worked in quite a variety of industries: automation, process industry, automotive, and the nuclear industries, and offer quite a variety of consulting services. I'd recommend, if you can, take a look at our website and see what other kinds of consulting and safety and cyber-related tools and offerings that we have that could assist your organization. There are quite a few reference materials that we have available. They're listed there. The one that probably best applies to this webinar is the one that you see on the left there, Practical SIL Target Selection. That reviews the safety life cycle, which provides a good foundation for the security life cycle, and specifically talks about hazard analysis, which is the focus of this particular webinar. We are ANSI certified as well as A-class certified. The ANSI certification provides for a detailed study of or ANSI comes in and does a detailed review of our processes and procedures and certifies us to those and to the ANSI standards. The A-class certification makes us by obtaining that, we have what's known as a lab certification, which allows us to do a variety of communication robustness testing on the systems that we certify. And to the right there, you can see a Exeter certificate that we issue on the completion of a successful certification. Hal Thomas, the author of this presentation, has a number of years in the 36 or more years in the chemical industry with their products. He's been here at Exeter for about 3 years as a partner, a senior safety consultant, and is very actively involved in our cyber certifications. He has extensive background in consulting and has used some of our products here, specifically FACS, LOPAX, and some of the other process safety tools that we have, and he's very much involved in industry organizations, as you can see there also. My name is Dave Johnson. I've been involved in software engineering for quite a few years across multiple industry sectors: process control, the power industry, the pharmaceutical industry. I'm a fairly recent addition to the Exeter team. My involvement here has been primarily security certification. I am on a number of IEC committees, ISA IEC committees, that are involved in identifying standards related to security and safety. So the objectives of this course primarily focus on a methodology to perform a cybersecurity risk assessment, which is designed to identify potential hazards that can arise from a cybersecurity attack on a process control or a protection system. I'm sorry, I skipped ahead one slide there. We'll take a look at the inputs that are needed for that detailed cybersecurity risk assessment, and also review the overall cybersecurity risk methodology. I do want to emphasize that this is cybersecurity attacks within the process control environment as opposed to, let's say, the financial industry. We're dealing with ways of upsetting and disturbing or perhaps shutting down safety systems that are part of manufacturing operations. So to start with, let's take a look at the safety life cycle itself. As you can see, there are three major components of the safety life cycle: analysis, realization, and operation. It's the analysis phase that we're going to be taking a look at, particularly the analysis related to cyber. But the safety life cycle here gives us a strong foundation. So the first thing you want to do, both in safety and in security, is do a detailed process, hazard, and risk analysis of your system. In the case of safety, you want to allocate safety functions that will protect against those risks that you've identified, and create a safety specification or safety set of requirements for those safety functions that you are going to apply. Once those requirements are in place, then the realization phase is similar to many other realization efforts where there's a design and engineering, acceptance testing, installation, and various validation stages that cover those. Once the safety system is in place and tested, there you go into an operational mode where you're maintaining the system, coming up with modifications perhaps that you discovered during the course of normal operation, and then ultimately the system is decommissioned. So that's a high-level overview of a safety life cycle. Parallel to those activities, you have the yellow bars that are on the left and the right, management of functional safety and functional safety assessment. So these are the requirements. You're constantly looking at the safety requirements of your system and making sure that they're current. There's project planning, configuration management, and other related activities that assist in the entire project implementation. And then off to the right, there are a series of verification and testing activities that occur throughout the life cycle. Each phase needs to be tested to make sure that all the requirements are met so you can move on to the next phase. So that's an overview of the safety life cycle. If we now take a look at some details of the cybersecurity life cycle, you can see that it parallels in many aspects. In other words, there's an assess phase, which is like the analysis phase, implementation phase, which is the same as the realization phase previously mentioned, and then operational phase, or the operate and maintenance phases. And again, you also have to the left that long bar, which are phases and activities that are involved and across all phases. The focus of this webinar today is on the green boxes that you see on the top. So we're going to take a look at process and plant design and scope, the definition of your system, zones and conduits, which are something similar to the process and instrumentation drawings in a control system. We're going to be doing and studying how to go about doing a high-level cybersecurity risk assessment, and then a process hazard analysis on that system to identify requirements for protection against the cybersecurity vulnerabilities that your system may have. So looking at the analysis phase of the cybersecurity lifecycle, we start first with the cybersecurity risk assessment itself, which involves the scope definition, so in other words, being quite clear about exactly what equipment is involved in the analysis that you're doing and the equipment that you're going to be protecting. You want to do then a process hazard analysis, a hazard and operational analysis, and a layer protection analysis on that cyber system. The result is a risk assessment, which in turn identifies the security level requirements. And then you ask the question, do the requirements meet the corporate risk criteria? And as an input to that question, you go to your corporate tolerable risk guidelines, which say things like there must be minimal damage to equipment as a result of cybersecurity attacks, minimal loss of product, minimal or no loss of life as a result of cyber events. And you cycle through that process until you have adequate requirements developed. As an input to the scope, you're looking at things like corporate site policies and procedures, project-specific requirements, again, your zone and conduit drawings, which identify logically the interconnection, communications interconnection of your system, any regulations and standards which might apply. You can see under standards there are listed 62443. That's a set of requirements which are used widely and in the process of being defined, used widely in the security industry. So the detailed cybersecurity risk assessment inputs that are needed, as we mentioned, the cybersecurity policies and procedures, and they're the basis for the recognized and generally accepted good engineering practices, RAGAT. So 62443 does a great job of identifying procedures and that are needed in order to, or identifying good engineering procedures that are needed to achieve these goals. You need to have that high-level risk assessment results, your zone and conduit drawings, and any HAZOP or LOPA inputs that may have been previously executed. So let's take a look now at an example high-level cybersecurity risk assessment. So as you go through with your team and identify threats, you can see on the left there that there are some potential threats. Data modification, data theft, potential denial of service, introduction of malware into the system. And as you proceed through the analysis, you want to identify possible causes associated with that. So data modification could have been done by third parties, disgruntled employees, or malicious employees. It's likely, so these are obviously of a concern to the process control system. The likelihood is that they are low demand and perhaps the consequence and severity, let's say for this example, is identified as a medium consequence. So the whole idea of this exercise as you go through data theft, denial of service, and malware is to take a look at those consequences and Pareto them and determine which are the very high and high potential threats that require mitigation. These are the things that you want to work on first. So this table identifies means to address those high-level risks and gain insight as to what needs the initial detailed risk assessment. So one of the other key components of your risk assessment is basically a snapshot or a clear understanding of the interconnections within your system. So here's an example zone and conduit drawing. As you look at this, you might see some pretty significant problems with it. Ideally, you come up with these as a result of your network engineers going around and basically determining what the interconnection is of the components within your system. Now this shows in this particular drawing that you have a direct internet connection to your field I/O. That certainly does not seem to be a good practice. Likewise, you're bypassing your DMZ by connecting your business site local area network directly to your I/O also. And the contents of the DMZ doesn't seem to be present. So someone at one point apparently decided in this environment that a DMZ was a good idea, but apparently didn't build in any equipment to actually perform the functions of the DMZ. So you can see that this particular zone and conduit drawing is fraught with all kinds of problems. Hopefully, when you do a zone and conduit drawing of your own system, you'll come up with something that looks a little bit better than this one. So we want to leverage that process hazard analysis and start asking some questions. Are the HAZOP or LOPA initiating events vulnerable to cyber attack? So are any of these protection layers that you put in place vulnerable? Because a protection layer that's vulnerable, that is somehow damaged or disabled, will then no longer provide the protection that you're anticipating. So again, are any safeguards vulnerable to cyber attack? And what are the consequences that are associated with the risk when they are in fact vulnerable? So if your system no longer has these protection layers in place, your system is now vulnerable. So there's a methodology that you want to go through as you're doing this analysis. And you want to do that high-level cyber risk assessment, initially by determining the scope. And let's take a quick peek at the next slide, which identifies the scope here for our assessment. What we've done is eliminated the DMZ in the previous drawing because there were no components there, and also removed the corporate enterprise from the scope of the project. So the zones that we have for this analysis are the site business LAN, the control room zone, the safety instrumented system zone, and the field zone, as identified by the blocks within the dotted lines. So now if I go back to the work process methodology itself, we've created the zone and conduit drawings. And when you put your team together, you want to make sure the information is available ahead of time to your team. And then you start looping through a process of zone by zone, node within a zone, and then threats to that node within the zone. And for each threat, you want to document the cause. The example was in the previous table: denial of service, loss of data, data corruption. You want to identify all those causes, document the consequences, identify any countermeasures, and come up with a resolution or mitigations for those countermeasures or as part of the countermeasures. And then you ask, are all the threats evaluated? Then are all the nodes evaluated? And are all the zones evaluated? And out of this entire process, you come up with a series of cybersecurity recommendations. Now, there's sort of a rule of thumb that's in the practical SIL selection handbook that I mentioned earlier, and that's the 20-20-20 rule of thumb. So the third 20 in that rule of thumb is 20 years of operation. Now, in order for a system, so a likely rule of thumb for a system that has 20 years of operation, you will most likely have 20 months of realization or the building of that system. And in order to identify the requirements, you'd most likely have 20 weeks of analysis that goes in. So 20-20-20 is 20 weeks of analysis, 20 months of realization to support 20 years of operation. Now, the analysis in this particular rule of thumb is not only the cyber analysis, but also the safety hazard analysis that's done on the entire system. So this gives you kind of a rule of thumb as to the effort involved. So obviously the cyber portion of the analysis, cyber is just one portion of the entire system analysis, but it gives you some idea of the effort that needs to go into the entire analysis process as identified by this workflow for a system that very likely will have many years of service for you. Again, the zone and conduit drawing that we previously discussed. So there's a lot of information that comes out of these analyses. You can compile the information into various documents, spreadsheets, or databases. Exeter happens to have a tool that can assist in this process. Actually, there's a tool called FACS, and then its counterpart, CyberFACS. The FACS tool does a similar analysis for a similar safety analysis. CyberFACS is the tool used in this kind of analysis. It happens to offer some recommendations to lead you through the process and helps you organize all the information that comes out of the analysis which is done. So that's where these screenshots come from. And you can see initially you want to take your zone and conduit drawings and put them into the tool, and you can see them listed on the left-hand side there. The process zone, field equipment, and the business zone that we had previously identified. And within all those zones, you have various threats that are possible that you've previously identified. This next slide shows those threats and the causes associated with the threats, and then associated consequences. So any given threat, let's say by a malicious third party, which in this example could potentially release toxic byproducts or cause an extended plant shutdown. Those are the consequences of that particular threat. You want to list all the ones that your team comes up with, put those in place, and then go through identifying the consequences associated with those and potential countermeasures. So countermeasures would be, well, what are you going to do that would help prevent that disgruntled employee, let's say, from coming in and causing damage to your system? Well, you can have frequently rotating passwords, or you can have multiple authentication. And in the case of any third-party software which could be introduced to the system, put together an antivirus program where your systems are regularly updated with antivirus software, or perhaps install additional internet firewall and additional firewall protections. So again, this tool helps you kind of organize this information. You can do it by other means also, but the most important thing is to, again, identify all the possible threats, causes, the consequences associated with those, and then countermeasures. So you can also put together descriptions and recommendations for what you can do with those countermeasures, and those then become your set of requirements that go into your successful system or successful mitigation strategy. So if we go back again and look at the overall requirements for success in your cyber analysis, you need to have accurate information about your process to start with. Your zone and conduit drawings need to be correct. You need to have a clear understanding of corporate goals, tolerable risk, any standards or regulations that your industry needs to listen to. And you need to have a technical team that is well familiar with these requirements, understands your existing system, and has a good, clear knowledge of cyber risk assessment methodologies. Ideally, you want a team of more than 2 people, but perhaps less than 6 people. The team starts getting too large, and it could kind of bog things down. But you do need the experts to go through and be able, you need individuals who understand those threats, understand potential mitigations, and ways in which you can deal with those by putting countermeasures in place. And again, that methodology, we'll go through that once briefly again, determine that scope, get your drawings together, and then go through individual zones, the cyber nodes that connect to the zones, and then any threats associated with those, and come up with your set of security recommendations. So in summary, you want to make sure that the risk assessment is an integrated part of your overall process hazard analysis and the work process associated with that. The initial scope should build on a foundation of recognized and generally accepted good engineering practices, standards, and procedures. Many of those are identified in the series of standards known as ISA IEC 62443. A high-level cybersecurity risk assessment allows the detailed risk assessment to focus on what's important. This is the initial assessment of your risks and Paretoing of the risks to determine those that are high, those that are low, less consequence. And the detailed cybersecurity risk assessment identifies weaknesses in the proposed or existing design or operation relative to the risk. So for those of you that are starting in brand new operations, greenfield, otherwise known as greenfield operations, you have a clean slate, and you can do these analysis from the start and build your implementations in from the beginning. Unfortunately, my guess is that many of you are involved with existing installations, and you're trying to put together a cyber risk assessment or a cyber strategy and overlaying that onto existing systems. That's a difficult task. 62443 will provide you with some good guidelines to make that possible. So, are there any questions? That is basically the presentation. I've gone through the methodology, the inputs to the methodology, which you might expect from the output of that methodology. My contact information is on the screen if you wish to send an email to me or to Hal Thomas should any other questions arise. I'll wait just a moment to see if any questions come up. Looks like I have a question here. What is the difference between the safety life cycle and the security life cycle? That's a very good question. Thank you very much for that question. They are similar in that both have analysis and implementation and management or operational phases. One of the fundamental differences between the safety life cycle and the security life cycle is the safety life cycle starts with potential random or systematic failures of the system. You want to look at potentially the existing equipment and what failures could occur with that equipment. Now, a security analysis or a security life cycle starts with the assumption that all your equipment is working fine and there's no failures associated with the equipment. But you're looking at ways in which people can maliciously break into the system and interrupt things that are going on. So it's a different perspective. It's not a matter of the equipment failing, but a matter of people breaking or outside entities being able to break into the equipment, break into your system. Both start with hazard analyses, which take a look at a potential loss of equipment, denial of service, loss of life. But in one case, you're looking at potential failures of the system, and in another case, you're looking at ways in which people can potentially break in. I see another question come up here. Thank you very much for that question. It's how do you define a systematic failure? Well, let me look at both definitions, random and systematic. Random failure is identified as a piece of equipment that fails itself. For instance, over a period of time, perhaps you will get components, let's say semiconductors, other components within the system that could potentially fail. So as a part of your design and making your equipment hardened, you want to make sure that your system is designed with high reliability components. So any failure, potential failure of those components would be what's known as a random failure. A systematic failure, on the other hand, is a failure that largely occurs as a result of some kind of a design error. So this could be potentially a software bug in the system, or it could be a matter of not selecting the correct component for an environment or a particular loading requirement. You're expecting a 2-watt load on a resistor and you only have a 1/4 watt resistor in place. So that wouldn't be a random failure of the resistor, it's a design failure. So that's what's considered systematic failures or design errors. Random failures are failures that occur just because of fundamental failures that occur within the components of the equipment itself. Are there any additional questions? I'll wait just a moment to see if any come in. Thank you. Yes, you are most welcome. Well, seeing no additional questions pop up on my screen here, I'd like to thank you very much for attending the webinar this afternoon. If you have any additional questions, you can see the contact information there. Be glad to answer any questions offline. Let me again encourage you to take a look at the Exeter website. It's a tremendous amount of resources available there, potential training if you're interested in finding out more about and getting a deeper understanding of some of these concepts. Again, thank you for joining us this afternoon, and have a good day.